Welcome. I think you're in the right place. Good. Right, rise and low. You don't need to know about me. You've got enough on there. What you need to know about is what we're going to do for the next 50 minutes. And it's some stuff. And then maybe a bit more stuff. Have you followed the flow that's going on here? It's all about stuff. Why have we got possibly in here? Because we may not do that. And of course, because there's a flow, if we don't do that, then we can't do that. And Q&A at the end doesn't always work. Occasionally people like to ask questions during. And I think, yeah, okay, so let's have the sort of Q&A during. If they seem to get a bit long, then maybe I'll close it down. But let's see how it goes. Let's be a little bit interactive here. Perhaps given the bizarreness of the title, perhaps ought to have a few definitions. And so here's a couple of definitions for data flow, moving data from one transformation to the other. I think that's probably what most people would say is the right definition for data flow. The Javaverse, as opposed to the universe. Java is only a very, very, very small part of the overall Javaverse. And in fact, in my universe, Java's gone. Just not interested in Java anymore. The Java platform, however, remains very interesting. And it remains interesting because of languages like Kotlin, Ceylon, Groovy, even Scala, Clojure, and so on. There are many other languages. These are just the principal ones, other than the one that no longer exists. Tension. Oh, never mind. And I'm guessing people are fairly familiar with bin tray, JCenter, or whatever they call it this week, Maven Central, and that sort of stuff. The place where you can never get an artifact to go, Maven Central. The point here is that the Javaverse is very big, and Java is only a very small component of that. I want to expand a little bit on data flow, though. And if you go, as almost everybody will, to Wikipedia, because as we know, everything on Wikipedia is true, just as everything on the web is true. Well, actually, data flow is fairly well defined here. And I've just lifted those three. This is copy and paste, these three items off the Wikipedia entry. And it's all about stream processing. Well, yeah, I think data flow is about stream processing. Reactive programming. I think this probably is the fad and fashion of this 5-year period. If you're not reactive, you're clearly not cool. Certainly not hip. Despite that sort of aggressive position, reactive programming does have a lot going for it because it's about making the software better for the users. That in itself is a good reason for having reactive programming as a trend. But there is actually nothing new about reactive programming. We have actually been doing it for about 50 years or so. The fact that it's a new fad and fashion doesn't matter. It's getting good stuff to the front lines. But I would say that data flow isn't reactive programming, and reactive programming isn't data flow per se. They are intimately related, and I hope by the end of this 46 minutes, then we'll have a shared agreement on that point. Is data flow about pipelines? Very much so, except that would imply a very one-dimensional view of the universe. And data flow is not one-dimensional. It's very much multi-dimensional. Data flow programming promotes high-level functional style. Well, yes. Anybody who has done any RX type stuff will have come across the fact that observables, map, filter, reduce, and all that sort of stuff, straight out of classic functional programming. Just for the record, really, gparse is the one true way of doing this. To fulfill the reason for that, go and have a look at the website. You'll discover why I say that. Akka is really more or less just about actors these days. Nothing bad about that, but it's only about actors. And Dataflow is about much more. And in fact, actors and Dataflow are different. And this is really about Dataflow. Quasar, I'm getting quite interested in Quasar. It's not as good as gparse, but it's still not bad. RX I've mentioned already. Apache Spark is here really as one look at the future direction of where all this data flow is going and why anybody interested in computation is going to end up doing data flow things. Because you could relabel this Hadoop or something like that. It's basically a data flow system underneath. Well, a little bit of philosophy for 43 more minutes. A program is a way of transforming n inputs to m outputs. If n has the value 0, yeah, that's fine. If m has the value 0, you think, rm star, please, because there is absolutely no point. Inputs here might not be values, they might be streams, they could be hardware. I know that's hard to believe in a Javaverse, but there is hardware out there, and you might want to interact with it. So we need an example. And because, we've only got like 42.5 minutes left, we need to keep it small. It's an example. It's showing the way. From here is a springboard. So, Java's going to have to exist for a little bit longer. So here is just 3 Java functions. Obviously, there's going to be a class out here, because obviously Java is a class act. And we've got some curly braces in here because it's a curly brackets language and so on and so forth. But for the next couple of minutes or so, all that really matters is we've got these 3 functions, F1, F2, F3. And we can do things with them. And here we are executing F1 and collecting the result. Executing F2, collecting the blah, 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 blah. Now, a quick show of hands. How many people would think they'd write in this style? Yeah, 1 or 2. Yeah. For those people who are going, okay. The style here is that you are immediately assigning to a final. Single assignment. Java is a single assignment language. The fact that most people in the universe, A, don't know that, or B, don't do that, is one of the fundamental problems of Java. Java is a single assignment language and should be used in that way. And this is actually quite data flow oriented. Oh, let's have a picky. Pickies are always good. So we've got a picky. We execute the function F1 on some values coming in. The values go out. We happen to store that in I1 as a mechanism for hanging on to that value in that particular sequence of code. But the most important thing was that it was input to F2, which output a value we stored in I2 and ends up with executing F3, and out it comes into I3, and so on and so forth. So in some sense, this code is an exemplar of a functional viewpoint and a data flow viewpoint. And you're thinking, I'd have written it like that, wouldn't I? Now, let's be honest, most Java programmers out there probably would have written this code more like that than like that. And bizarrely, this trivial little example is showing us one of the fundamental viewpoints between data flow thinking and stateful thinking. Here we've got a state that we update and change. Whereas here, we execute functions, capture the values, we make a binding between a name and a value. And probably not many of you out there have studied Wittgenstein. The point is that if you've got a name for something, you can talk about it. Here we're pinning a name to a value, and that's it. Here we've got updatable state, and that is part of the problem. It's updatable state. I think I've waffled enough about that slide. Now, many people, functional, remember we started out with Dataflow would bring about a functional way of thinking. So the functional people will say, well, why don't we just execute F1, then F2, then F3? Get rid of all the state completely. Yes. No. The values are still there. This is still an expression of this diagram. It's just that we didn't give the values names. They were anonymous values that were passed some way, we don't know how, between one function call and the next. But it's still a data flow that's going on there. It still meets the requirements of that diagram. No, let's not go there. You are not compiler writers, so let's not worry about that. Oh, okay, we talked about different languages, different expressions. How about Frege? This is not Wittgenstein, it's Frege, completely different philosophy. Never mind, that joke's not going to work. Here is a Frege program. Well, it's those three functions again. Look how simple it is. None of all this, may I use the term bullshit, associated with the Java code? There it is. It's just F1 is a function that doubles a value, etc., etc. If you don't know of the words point free and partial evaluation, you don't need to admit it now. But go away from here very quickly, probably using Google, look them up and spend a few hours thinking about what they are. Because particularly the partial evaluation is very important. And point free less so perhaps, but in this case it's really nice. We're defining a function without any variables at all. We like this stuff. Also, Frege has no class per se. They're top-level functions. Why do we have to wrap them up in classes? That's just a Java thing. So here we have a function showing us exactly the same as the Java, and actually it compiles to exactly the same bytecodes underneath, near as damn it. We have the resultant expression, and we have various bindings being made. Yes, they are names, but they are definitely bindings to values. Single assignment. Pause. Question, sir.
This looks a whole lot like Haskell.
Funny you should mention Haskell. Yes. First there was Haskell, then there was Jaskell, and it died. And then there was Frege, which was slightly different from Haskell, but now has the determination to be Haskell on the JVM and is succeeding massively. So yes, it is Haskell.
You define success.
That's a bit of a problem, isn't it? Because one of the goals of Haskell is not to be successful. Curses, Simon's going to be really railing at me next time we meet for making Haskell successful. Pity. Never mind. The point here, though, is we've got single assignment because these are bindings to values. You can't update them. But to be honest, no Haskell or Frege programmer would write this code like this. They would probably write it more like that. Actually, they wouldn't write it like that at all. Far too Lisp, far too many parentheses. They'd write it like this. Actually, they wouldn't write it like that at all. A real Haskell or Frege programmer would almost certainly write it like this, saying, compose the functions f1, f2, f3 into a single function and then apply it. So actually what we've now got is that, which is completely not Dataflow. So you're thinking, okay, there is method in the madness. Just to introduce the math, just in case nobody believes it, that is an axiom in mathematics. You can go away, it's provable, etc., etc. And we do not need to be afraid of maths. So this is actually more like the sort of Haskell or Frege code that you would see if someone were being more explicit. They would say, okay, the result is f of I, where f is some point-free composed function. Doesn't need worth, it's not actually worth saying that, is it? No. So what we want is infinite streams. The infinite is where we really want to be. None of this big data stuff. We want infinite data. But we need to go in stages. We can't go straight to infinity. So let's go to big first. And we've got to be groovy. It's not possible to have a Russel Winder talk without a mention of the word groovy in it somewhere. So here's groovy. Nowhere near as good as Frege, but a damn sight better than Java. So here's us do. Oh, this is horrible. This is absolutely awful. Oh, this bit's nice. Yeah, that's nice Dataflow. Nah. And if we went here, at least we'd be being consistent. Horrible, but consistent. So consistency is not everything, because horrible just out-trumps consistency every time. Even if we went down to this, it's horrible. Why is it horrible? Because we've got state. Absolutely. We are constructing values in an array. This is horrible. Can I overstate how horrible this is? Sadly, 95% of people's code looks like this sort of thing. Bits of niceness surrounded by awfulness. Let's actually go. Where's the pen gone? Oh, there it is. This is really horrible. This is red horrible. So how might we get... This is supposed to be groovy. Well, yeah, it's just all that state. It's not good. So what you could end up with is doing this stuff. And you think, Java... No, it's not Java. It's the streams out of the Java platform. This is good stuff. We like this. And people are thinking, oh, yeah, he's creating a stream, and then he's doing a map, and then he's doing another map, then he's collecting it all together. This is looking a bit pipeline-ish. Pipeline, data flow, looking a bit like this. No. No, it isn't. It looks like it, but it isn't. It's actually that. Because if you actually look at the implementation behind it, you've got the words intermediate operation, terminal operation. And what's happening under the scenes, of course, is that you are composing the intermediate operations into a single operation. So actually, all this stream stuff, is being done with sort of composition, effectively, behind the scenes. But you can still think of it as a data because it says .map, .map, .map. So you can think of this as the goal. This is data parallelism in the extreme. We are mapping into some data structure with that composed function. That's actually more of a model of what's going on with streams. A model of, not exactly what's going on behind the scenes. I guess the people who mentioned the word Haskell would like this particular slide because it describes the way of doing data parallelism behind the scenes.
You don't even need the L, do you?
Sorry, could you be a bit...
You don't really need the L, do you?
we don't need the L, is the point being made here. If we were doing it point free, we could just get rid of that and get rid of that, and it would be even better, perhaps. Yeah. We are defining a function as a map over a composed function. Oh, this is good stuff. This is functional paradise. So I thought we've had 3 languages. This is not enough. Let's have some more. So let's do Kotlin. Why Kotlin? Because. So here's Kotlin type way of doing things. Again, top level functions. As we can see, this has got to be the best language on the planet at the moment because we can have lots and lots of fun. Come on, guys, wake up. So here's Kotlin using streams. Some of the sub-agendas going on here is that these languages can do better than Java everything you can do in Java. So there is absolutely no reason to stay with Java. You want to move as fast as possible because you're still working on the Java platform. You're just making your code that much more maintainable. So let's do this. Would that be one of these compositions behind the scenes in the streams? Yes, absolutely, because you are using the streams just expressed in Kotlin code. Would you do this sort of thing in Kotlin? Well, occasionally, maybe, yeah. Is that the speaker that's going, or is it my hearing? It is the speaker, okay. We are using top-level functions and mapping and so on and so forth. This is the functional side of things. You don't get to do this sort of thing in Java, though. Compose functions. Yeah. So if we're getting into data flow and functional, then Java really is a dead end. Streams in the Java platform, lovely stuff. But how would we implement compose? Yeah, that'll frighten a few people, I'm sure. It's almost Scala-ish, except a little bit simpler. But he's going that road, and you always hire cool people to do this and then hide them in a corner somewhere and just use the results that they deliver. Okay, 1 or 2 people are managers out there, they heard that one. Okay, so how do we go about getting really infinite? Because data flow is really going to be about huge data sets. None of this 6 gigabyte XML file rubbish. That's tiny stuff. We're talking about 200 or 300 terabytes per day type data. And if you think that's, well, what's the Bloomberg feed producing these days? It must be terabytes a day. I'm not really into finance, but LHC, Large Hadron Collider, for example, produces 6 or 7 terabytes of data a day. And you can't put it on disk fast enough. You have to actually ship it over the internet to get it out. That's potentially infinite. Those are the sort of numbers. And the one thing you don't do is map. That's just not an operation you get into because you've got to do the whole thing. We're talking about infinite things. So you tend to stick to doing things like reductions or windowing or just plain old side effects because that's all you get to do when you know that you've got an infinite amount of data more before you can do anything. So if you want to do maps type operations, you've got to do windowing. You've got to say, I'm going to deal with the last 10 items, the last 35 items. That's the notion of a windowing. A reduction is saying, I'm doing something cumulatively, taking some form of cumulative operation. And side effects, well, if we're talking functional programming, we sort of don't talk about side effects because that involves words like monads. And that generally turns most people off. An attempt at humour. So let's do something quasi-interesting. Cumulative means and standard deviations. I say quasi-interesting because a variant of this sort of problem is exactly how most hedge funds work. They just run with running means and standard deviations and then apply lots of weird and wonderful algorithms on top of it. But it's fundamentally a windowing operation over infinite streams. So not entirely unreasonable as an example. So here we have a couple of interesting equations which tells us about means and standard deviations. And remember, we want to do infinite amounts of data. Oops. So this equation is completely and totally useless to us if we want to do things with infinite amounts of data. By definition, requires a finite data set in order to do this. And so anyone who's been doing this sort of thing will immediately jump up and down and say, yeah, well, all we have to do is that. A simple transformation on the equation, which means that we get to do the summation independently of anything to do with this summation that's going on over here. Right, well, that's the equations over and done with. So, oh. Okay, so it's a hungry squirrel. Yeah, we spend about £2 a day feeding that one. And the other 7. Long story. Anyone who's interested in squirrel, we can talk to them about that afterwards. But can we look at code now? No, we can't, because we need an architecture of what we're doing here. So we need a little architecture. What we've got is this. Okay, I told you I was going to keep things small so we can get it all on one slide and so on. I run the risk, of course, of trivializing by using a small example. Please remember that this is an exemplar of the ideas that you then take out and apply to bigger problems. So what we're going to do is we're going to have this, which is a splitter. So its only job is to take an item of data and feed one that way, a clone that way, and a clone that way. Classic demux type thing that's going on here. So we've immediately got more than one dimension going on here. So we've entered into a 2-dimensional data flow world. Each of these is a simple transform, and we've been used to those over the last 20-odd minutes. That's fine. Now, if this was doing F1, and this was doing F1, and this was doing F1, you'd either be in a motor race, or you'd be talking about map reduce. Yeah? Oh, sorry. Map reduce TM. We have to remember that in this jurisdiction, map reduce is a trademarked symbol. But if I was to say that this is a map and this is a reduce, now I'm okay. So there's no trademark on that. And these terms have been used for 60 odd, well, no, about 360 odd years. Because since the beginning of calculus. So this is in effect a big parallel map, if all the functions are the same. But that's the whole point of this data flow problem. They are not. What we are going to be doing is counting values in here, creating a sum in here, and creating some squares in here. Remember those equations? We need to calculate the sum, we need to calculate the sum of squares. So for each item coming in, we calculate a cumulative count, a cumulative sum square. We then send them off to this synthesis object, which then calculates some result out of here, and it's going to calculate x bar, s, and the number of degrees of freedom. So you're accumulating your numbers. To do this as running, to have a window instead of doing it over the whole data, it's just a change in the little algorithms that are going on in here. So these are stateful in some sense. They're not functions in the maths sense, they're not functions in the functional programming sense, but we're still using a functional programming attitude and functional programming approach to them. So, do people feel relatively cool with all that? So I shall now change to showing code, which will necessitate a few rearrangements on down here. The first one being is that a big enough font? Actually, why don't I separate out that so it's on its own? No. Is there a bit too much show through of the background? Yeah, okay, so maybe I should change the background. If anyone's wondering, it is the London Wetland Centre, which is just a very, very cool place. That's probably going to be better, isn't it? So we should make the fonts bigger. And of course, because we're using Emacs here instead of an IDE, there's none of this indexing going on. So we don't have to wait 10 minutes for it to finish indexing. I do use CLion and PyCharm and IntelliJ, so I have drunk the Kool-Aid, just not for presentations. Okay, so this is how you might do this problem just with state. Okay, so this is just trying to show the dark side of how you might do it. It's also very simple, and that is part of the seductive nature of the dark side, is it's simple. The problem with the dark side is you end up like Darth Vader or someone like that, and nobody likes you anymore. So how might we do this with... oh, that's running stats. That was a bit naughty of me, because I was supposed to be doing cumulative, wasn't I? Spot the difference. We're not creating a window, so it's even simpler. This is cumulative. Apologies for showing the wrong slide initially. So we're just running cumulative statistics here. So we're just issuing a new list. Isn't Groovy wonderful compared to Java? The answer is yes. So we're issuing a tuple, if you like. It's actually a list with the mean, standard deviation, and the degrees of freedom once for every new item coming in. So a fairly simple, straightforward problem. Exactly that scatter, gather that was going on. So how might we do this with... what do we got here? We've got some options. Stats data flow. That's what we really want. Data flow operators. Let's make the font a bit bigger. How's that? Folks at the back? Folks at the front can see it anyway. The people at the back have the casting vote. Is that a good size? Yeah, I'm getting a nod. Okay. So what we're doing here is we are constructing the network. So you manually construct the channels that you're going to connect together. And then, here's a splitter. So that one line is that first box has one input, and it splits out into 3 in this case. So we've given a list of channels, and for every item on the input channel, I should actually do this way, shouldn't I? For every item on the input channel, it sends to the output channel in this list. So that's a 1 to 3 splitter. Pause. There's a question over there. For the video and the sound, I've just been asked to scroll up. It's because this is not, we're not, yeah, you know what the problem is. So having shown the top bit, whoops, I need to do that. So we've now got at the top a couple of, well, there's the splitter that I was talking of. So for each item on the input, we put the same item, a clone of it, out on each of those outputs. So here's an operator. Remember the boxes? So we had those boxes like that. So here's one of those boxes. In fact, it's the top one, the counter. So for every item coming in, it just counts. That's its job. Yes, we have a bit of internal state. Yeah, fine. We have an input, and for every item on the input, we execute this code, and the last item of the code is to put some output on that output. So given an input coming in, we count it, and we put the result out on the output. Seems like a bit of a function, but it's stateful. It's a stateful operation. And the others down here is very, very straightforward. In some sense, we're summing. This is boilerplate, that's boilerplate. A little bit, yes. One admits that there is some boilerplate here to all this. Here we're doing the squaring before we do the sum. And then we've got something which is really very, very mean. I didn't lead up to that one very well, did I? I was worrying too much about making sure it was in the right place. Slight pause. There's a question over here.
Before, when you were showing the boxes, and the 3 boxes in the middle were doing the same function, it's known as matrices, as you said.
Yeah.
When they're doing different functions, what's that called?
It's just Dataflow in this case. Yes. Sorry, I should have repeated the question because your voice was probably not on the audio. So it was, just to repeat that one, given the original diagram we had out here, the question was when this was F1, 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 we sort of said that was a MapReduce type thing going on. Is there a specific name for F1, F2, F3? Answer, no, it's just Dataflow in this particular case. And the crucial beauty of this is you can parallelize it as much as you want. Well, for every one of these things, you can have a separate processor, separate thread. However you do your parallelism, you can make them separate. Let me clean that up a bit. In fact, let me go down here to the diagram itself. This can be on a separate processor to this because they are completely independent activities going on. Where is the concurrency control? Where is the parallelism control? It's at the point at which you receive the data. So there are no locks, no semaphores, no, all of that operating system paraphernalia is nowhere near our application here because it is completely unnecessary. The very nature of the Dataflow model has synchronization built into it. So all of these single-threaded. it's actually quite important that these are single-threaded. Because if you start doing multiple threads in there, you've ruined the whole point. You've not deconstructed your problem into a proper data flow world. There are actually a number of different data flow models. Let me do that one again. Communicating sequential processes is almost certainly the most famous one because it has a name. And Sir Tony invented it, 1977-ish, really. The book was, I think, 1982, 1983, sometime around then. So it's not exactly new, but I suspect many people haven't really come across CSP in this room. Well worth looking up. Groovy and GPARS. Remember GPARS? Yeah, CSP. Good stuff. You can with Quasar. It has what they call fibers and channels, and between those you can make CSP. So it's not just GPARS that's doing this. There are lots of technologies coming along that are giving us this capability. Just to round off on this little section, we've got the last of those, the one that's collating, doing the reduction, is here. So it's got 3 inputs. It only triggers its code when it's got a result on each of those inputs. There's our synchronization. The body of our data flow function only executes when the data's ready. That's the beauty of this model. It's single-threaded. You have no worries about what's going on in here because you know the notion of shared data is not going around, not there. You can have state, yes, but there's no sort of locks and semaphores and things. Another pause. Question there, sir.
I was just wondering how you choose the type of color.
The question there is about types and how do you choose types.
In the infinite case,
Particularly with the infinite case. The answer there with GPARS is that you're effectively doing this type free. You don't worry too much about types. Because the origin of Groovy was as a typeless language. Well, it does have types. It's if you put types there, it checks them at runtime. Or you can do the static typing. So there is an option to do static typing in Groovy. And then there's also fully compiled out Groovy. Now the difficulty here with GPARS is that it is focused entirely on a runtime typing going on here. So if you start doing horrible things to your double in your code here, at runtime it will give you an error. Now for some people that's a good thing, for some people that's a bad thing. Using Kotlin and Quasar, you would have fully strong typing at compile time. And so using slightly different infrastructure, you will get the typing that I think was the point of the question. With GPARS, possibly now, possibly forever, it's difficult to get that sort of compile time type checking that I think was the tenor of the question. Has that answered the question?
I think the question might be about the overflow of the int. This is an infinite stream.
Ah, right. Apologies. I've answered the wrong question. Thank you for the clarification. The clarification is really, if I've got an infinite number of items, eventually the degrees of freedom of the problem will sort of blow up. Yeah, Yeah. In which case, what we have to do in here is big integer. And actually, if you deal with this properly, you'd be using big decimals anyway, and big integers. And it would all slow down a lot, yes, but it then wouldn't overflow. Hardware numbers are the bane of all computational life, always. Yeah, maybe I'll just leave that one there for now. I think I've answered it, and I'm beginning to waffle, I can tell. If I've not really answered it, maybe you could catch me after we've finished here, and I'll give a proper answer. Another pause, there's another question here.
Is it possible to specify that I need 2 items from one input per one item from other?
Actually, yes, it is. It's not easy in GParse, and we're actually trying to study that problem here. Because GParse, as it's now out there in the artifact, is 1.2.1, and it's a JDK 7 thing, and we need a proper JDK 8 thing, and we're going through a lot of the thoughts about how to deal with streams. Should we actually compete with streams? No. How do we integrate with streams? That's an interesting problem at the minute. And having patterns of saying, oh, I need 2 items from there, 3 items from there, and 1 item from there is an interesting problem. And it's not solved by this particular model. It's very easily solved by extensions to actors, where actors don't have one mailbox, they have multiple mailboxes. And CSP allows for that. And so the Dataflow model in general allows for that. What I'm showing here as a Dataflow implementation doesn't allow that per se. There's another question over here.
I'm still also agree on your previous point regarding synchronization. How does the aggregate function get called? I mean, at some point, we need to make sure it has the necessary inputs.
Yeah, because the underneath infrastructure has been told that there are 3 input channels. So you only trigger execution when you've got an item here, and an item here. That fact, the arrival of the 3rd item, triggers the computation. So just nipping back to the code, we have 3 here. We must have an item off each channel before we execute this closure. And that's the point of synchronization. Still got a few frowns there. I'm conscious maybe we should take this one, I was about to say offline, but no, we need to be sort of talking to each other, but outside this particular scope, I think. So if I may, I do actually need to round off here. So we've looked at some code, which is good, because when we talk about code, we actually like to see code. What's the overall message? Lots of small, single-threaded pieces of code. Programmers are actually very good at writing single-threaded code these days, particularly using the right tools, which is not Java. But it's the combination. The functional programming people brought function composition as a way of doing these combinations. Dataflow is a way of composing your little single-threaded operations and the data flows between them and having synchronization that's effectively automated. It's sitting over the top of thread pools. Anybody managing threads explicitly is doing it wrong. There's just no way of getting out of it. Oh, unless you're writing an operating system. Then you're allowed to use locks and semaphores and so on. But anybody writing applications should not be doing that sort of programming. Yeah, and you can't do big data without parallelism, so that's a and it's really about the data flow, not about the state. And I think that over the last 10 years, if that's not obvious, then you need to go and have a look at the history, because it just is the problem. So I'm about to finish. But before I go, yeah, we had to have another squirrel. Sorry about that. The Q&A, well, we've had some, which was great, but it has meant that we've got about 30 seconds left. So as long as it's 20 seconds worth.
In Java, the function interface does have a default method after and before, but can also be used for function on position, I think. So you actually need Groovy for that.
Given that it's saying you don't need Groovy, I'm going to not answer that question. Actually, you're right. But I'm noticing that it's flashing red and white here, which is telling me that I need to be nice to everybody and say we should close this session off now. If we want to chat afterwards, I'm quite happy to do that. So for now, thank you very much.